Hey guys. So we're going to go ahead and start Unit 5B today, and we're going to be talking about volume in this unit. And there's several different ways that volume questions can be asked, but I can tell you this much. Uh, these are another very common thing to happen on the FRQs. So on the AB exam in particular, literally every year there's an FRQ that will ask about area and volume. We are going to review area a little bit, how to find the area under a curve using the integral, because we're going to be building upon that for different ways of calculating volume. And next week, we're going to start talking about the volume project that is all over my classroom. You guys will be making those soon. But we have some ground to cover first before that happens, so we're going to begin with the easiest part, which are volumes by the disk method when we're calculating those at axes. Okay, so let's dive in. So first, we're going to look over area. Okay, so the formula for the area between curves, we know this already in theory. It is in our TTK book somewhere. But the formula for area between two curves, or between a curve and the x-axis, is just top minus bottom, right? That gives you the area under the curve. When we very first started doing definite integrals, we were doing all those rectangles and whatnot, trying to approximate this, and then we realized it's the same thing as just calculating the definite integral. So we've got the area, the easiest way to think of this, if you're doing in terms of dx, right, we've got our left to right on our definite integral, and then just the top function minus the bottom function. And if you're not sure, let's say you're not using the calculator on this problem and you're not sure which one is top and bottom, as long as they're both in terms of the same variable, so in this case in terms of x, as long as they're in terms of the same variable, just do one function minus the other. And if it comes out negative, you did it backwards, stick a negative sign in front of it, and fixed. Voila. So this is if we are doing in terms of x, right? That we've got, some function on top, here's f1, and we've got some function on bottom, here's f2, and we want to find the area between them, from A to B, right? That's what we do, and we're, it's like we're doing all the little rectangles, right, this way. So we're doing top minus bottom. But we also can do this with respect to y if we have a different type of function. And this is actually going to start coming in more in handy, but also more important, because sometimes you're going to have to do stuff dy. Most of the time it's dx, but sometimes we're going to have to do dy. So if we're doing dy, we just need to make sure that both of our functions are with respect to y, right? And then also that these values, a and b, are going to be y values when we're doing it this way. So everything is with respect to y now, and that means that we need a right minus a left instead, because our y values for top and bottom, right, this is like if we have some function maybe this way, and maybe it's this region here, right? So if we're doing all of our slicing our imaginary rectangles this way, then we need to do right minus left to get the length of those, because the y is a and b, or c and d, or whatever we want to call them, right? Our y1 and y2 here that are going to be our top and bottom numbers, right? This is y, right? So bottom to top or vice versa. Okay. You can look back at your stuff from Unit 4B if you need to look more at area and area between curves. But now we're going to keep moving, because now we need to start talking about volume, right? So area, we know, is a two-dimensional, right? Area is about flat stuff. Volume is about 3D stuff. So now we're going to kind of start taking stuff into the third dimension. And there's two different ways that we do this in AP Calculus. And this week we're going to talk about one of those methods. Next week we'll talk about the other, and the other method is what the project is going to be about. So before we start talking about the calculus of this, we need to kind of look back at a little bit of geometry and volume of a cylinder. Okay, so a cylinder, right, has a circular base, like a can of soda, right? If it were perfectly cylindrical, right? We've got a circular base, and then we've got some height, right? And then a circle at the top. And all along the way, right, these are all circles, right? If you were to slice it, right, you would just get, a perfect happy little circle coming out of it, right? If you were to slice it like that. But if we were to think about the fact that this is a three-dimensional object, right, if we were to say, well, how can we get that out of the XY plane? Okay, well, if I had some constant, we're going to pretend that's a flat line, okay? Let's say this is the line y equals 4. I'm still getting used to writing on this board. So let's say that's y equals 4, right? And I'm going from, I don't know, 1 to 3, right? If I have this area under this constant curve, and that's an area right now, right? That's just, that's 8, right? But if I take this flat thing and I start rotating it around the x-axis, now this stuff is hard to visualize at first, and tomorrow, hopefully I'll be back, and we'll do a little bit of 3D modeling of this on our own. It's fun, I promise. But in this 2D format, stay with me as much as you can. If I took this and spun it around, oh no, hold on. And I spun it around, oh my God, this pen is being a pain in my behind. If I spun it around the x-axis, that's what I'm trying to say. Right, so it's like if you take a flat piece of paper and you start spinning it around, right? If you start spinning that piece of paper around, it's going to make a circle, right? So if I take this flat, 4 across the top, and I start rotating it, right, it's going to kind of make a cylinder, right? Because it's very difficult to draw this on the new board. I'm still getting used to this, I apologize. But it's going to make the three-dimensional cylinder if you take some flat surface and you start rotating it around. So that's the idea, right? We can think of any other cylinder that we have, as being like on an axis, and they took some flat thing and they started rotating it around to get the three-dimensional thing. That's the essence of what we are doing with what is called the disk method. It's called the disk method because if you take a cylinder and you slice it, you get circular disks, right? Like a CD is a flat circular disk. Now a CD has a hole in the middle of it, and we are actually going to talk about later this week what happens if there's a hole in the middle of it. We're not going to worry about that for now. So for now, flat, solid, circular, or other shaped disks. Oh no, it's doing the animation for me. Spoilers. Oh well, that's fine. Okay, well, now that it has spoiled it for me, here's the idea, is that we're not going to just be working with constants anymore, right? Obviously not. This is calculus. We're all about things changing and being curvy and weird and not constant. So the idea, right, is that if I were to take this f of x curve and rotate it, it would make kind of like a vase shape, right? And if you envision, and it's, I know my little animation's going over there to the side too, but it's going to make a little vase. So the idea is that I'm taking what was once just a curve on a piece of paper, right? And I am rotating it around a certain axis. Now we're going to start with the x-axis, and today we're going to talk about the x-axis and the y-axis, but later on we will talk about how to rotate it around different lines, right? Like how am I rotating around the line x equals 3 or whatever. So the idea is like what you see over here on the right side of the screen. We're making solids now, right? These are three-dimensional shapes. And here's the idea though, right? If I take any one slice of this it's still going to just create a circle in its own space, right? It's going to create that flat circular disc in its own space. As you see it kind of go through the vase over here, right? Those are all circles. If you slice it that way, they're all circles, okay? So we're building off the volume of a cylinder, which again is pi r squared h. And that pi r squared h, the pi r squared is just the area of a circle. And you're just taking the area of the circle and multiplying it by the height. In other words, how many circles do you have? So pi r squared h. That's very important. Okay. So suppose that I start with this curve. We're going to start with the curve y equals root x. Suppose that my boss at the Acme Rocket Company has assigned me to build a nose cone in this shape. So back in the day, before we had 3D printers, right, you could take something like this and you know you want to cut it into having that shape curve on the outside, but rotating it around to get a three-dimensional shape. So we put it in, you know, put the wood in a lathe and turn it around, rotate it, right? If you've ever watched someone doing wood cutting and they can rotate it around to get smooth little circular shapes, voila, here's what that would look like. Now, it's obviously not the same kind of cone that you are used to from geometry, so we can't just use a straightforward geometric formula, right? This upper kind of boundary up here, that's that y equals root x curve from before. The idea is that we have taken it and rotated it around the x-axis to generate this three-dimensional shape. Okay, so great. What do we do with that? How do we find the volume of the cone? Well, one way we could do that is to cut it up into a bunch of these little discs, these other slices. You can think of them as a rectangle that you're then rotating around, right? Just like we did rectangles before with Riemann sums. Okay, so if we've got these little rectangles that we are spinning around to make discs, okay, so the volume of each disc, well, if each one of these is an infinitely thin cylinder, just like we have our infinitely thin rectangles, right? If we're rotating it and now getting an infinitely thin cylinder, and the volume of a cylinder, again, is pi r squared h, then the volume of each of those cylinders is going to be pi r squared times h would be the thickness of the cylinder, which we've already said is going to be infinitely thin, right? It's going to be, in this case, that really small change in x, right? So what's r then, right? If I've got pi r squared h, and h being the height of the cylinder here, right, is that very small change in x, infinitely thin, so dx. Well, what's r? Well, if r is the radius of those discs, that radius as I go along the curve here is just being determined by y equals root x, right? It's just the height as you move along this curve from x equals 0 on the left to x equals 4 on the right. So in place of that r squared, come on animations, here we go. Okay, so r is the y value of the function, or in other words, it's root x at any given value x. So pi is just pi, r squared in this case becomes root x squared, and then the thickness of those cylinders, as we already said, is dx. So what it's saying here is the thickness of the disc is just dx. So the volume of each disc, all of them along the way through the whole nose cone here, is going to be pi times root x squared times dx. Okay, so if that's the volume of these, we have a lot of those, right? We have them going all the way from 0 on the left to 4 on the right. You see where I'm going with this? I have to add them all up. Remember that the reason that we have an integral sign is because it's a long skinny s. The s stands for sum. We're going to add all of these up. So we've got the definite integral from 0 to 4 because that's where we're looking along this curve. Pi, because that's coming from pi r squared h. So pi is there. I've got my r squared h. So again, r was determined by my function. And then dx, right? And in this situation, the dx represents the thickness of the disks. So if we actually solve this, well, I've got root x squared, so that's cool. That's just x. And then it's x to the first, so I'm going to increase it to the second power and divide. Evaluating from 4 to 0. Okay, 4 squared is 16 over 2, which is 8. 0 is 0. So big finish, the volume is 8 pi. So that's the idea. All of these are going to come back to the volume of a cylinder formula, right? So the idea, pi is just pi, and it's always going to be there. H is going to be either your dx or your dy, depending on what direction you're oriented in. The big thing, though, is r. It needs to be squared, and it's coming from, again, whatever your function is in your context. Whatever thing it is that you're spinning around to get this three-dimensional shape out of it. Okay. So this is called the disk method for obvious reasons. So the shape of each of those, right, is a flat disk. So this is called the disk method. There's a few different methods. We don't do all of them in AP, either AB or BC. There's a method we don't do called the shell method. It's in your book if you're interested. But we're going to do the disk method today and tomorrow. And then later this week, we're going to look at the washer method, which is a slight bit more complicated. So in general, our formula for these, if you're going around a horizontal line, is, again, these are easiest to remember if you just keep thinking about the cylinder formula, right? Pi is always going to be there. You're going to take whatever your radius function is, you're going to square it, and then of course there's dx in the back, and that dx is taking care of the h piece for us. Now this can be around a horizontal line, in which case you're going to do dx. But if you need to rotate around a vertical line, you're going to do the same thing, but dy, which we're going to look at in just a second, right? But dy, that means a small change in y is going to be the thickness of the cylinders because you're rotating in a different direction. So this is what I meant when I said the dx or dy is going to matter. Because if you take this same region and you rotate it around a different axis, you're not necessarily going to get the same volume. So you have to do it with respect to whatever axis they give you. It does matter. It does make a difference. Okay, so for this next one, we're going to look at one that's in terms of y. So we've got the region between the curve x equals 1 over root y, y values from 1 to 4, and the y-axis. And it's being revolved this time around the y-axis. Now, that's actually really important. You're going to need to be paying attention to what you're revolving about every time. That's really the first thing you're going to look for on these problems. Now, today, we're just doing the x-axis and the y-axis, and tomorrow we'll look at ones about other lines, as I said earlier. So if it's revolved about the y-axis, that means this is going to be a dy problem. Again, that's the first thing we're going to be considering each time. Now, I will say that the good news is, generally speaking, when these appear on the FRQs, they actually will go ahead and give you the graphed image so that you can see the region that is your area that you will then be rotating in order to make your volume. Okay, but sometimes on the multiple choice, they don't give you the graph, so let's figure that out. We're told that we're using y values from 1 to 4. Because this is a dy problem, they gave us the y values, but again, that's not necessarily always going to be the case, but because they gave us the function in terms of y, we're just going to take some y values from 1 to 4 and plug them in, right? So if x is 1 over root y and I plug in y equals 1, that gives me x equals 1, right? I plug in the 2, I plug in the 3, I plug in the 4. These are ordered pairs just backwards, right? So if I graph 0.11, then if I take this 0.707, right, because if I write that actually in the order to which we are accustomed, right, that's my ordered pair, really. If I'm thinking x, y is 0.7 and then 2, right, 0.57 and then 3, and then 1/2 and then 4. Long story short, it's going to look like this. So I've got my 1, 1, then I've got about 0.7 and then 2, about 0.57 and then 3, and then about 1/2 and 4. So our region is this region in here, right? We're told it's bounded by that curve and the y-axis, right? We've got our curve and our y-axis from y equals 1. That's our bottom number. Oop, that is not the pin. Okay, so 1 at the bottom here, and then from 4 to 4, excuse me, at the top. Okay, so the idea then, right, is that we need dy to be the thickness of our discs because we're going to be slicing this horizontally. Okay, so if we're using a horizontal disc, you'll see it's now drawn in over here. Okay, so the thickness of that disc now is a little tiny change in y, right? Because they're flat cylinders, we've got our little tiny change in y. The length of those, right, that horizontal length of that, again, is determined by our original function because that's what was giving us the height, quote unquote, of the curve, right, or kind of the width of it in this case, I suppose. So that gives us our radii, because again, pi r squared h. So that r is going to come from whatever's giving you the length of the discs, h is going to be dy, pi is pi. So here's our formula for this then. We're going to do the integral from 1 to 4. Pi, you can stick it in front of the integral if you want. It might be easier to always kind of stick the pi out in front. It doesn't really matter because that's a constant. Then I've got my r squared and dy. And that's going to give me the volume of the discs. There's two things that are very easy to forget in this formula. One of them is pi and the other is the square. It's very easy to forget to put pi in front of all of these, kind of like plus c back in the day. And it's also very easy to forget to square these because we're not used to having to do anything to what we're putting in the integral. Now we are, right? Because now, again, we're going back to this formula that we're basically modifying with calculus. Anyway, if I have 1 over root y and I'm squaring it, and I square the top and I square the bottom, that just becomes 1 over y. Okay, well, if I have 1 over y, that's, you know, the same thing as y to the negative first power. Oh no, I can't do the power rule because I can't divide by 0. Who invited logs? Who invited that guy? Nobody likes that guy. So this is going to be pi times natural log of y from 1 to 4. We can plug in the 4, plug in the 1. Okay, and it's just pi times both of them, right? But natural log 1 is 0. Cool. And pi times natural log 4 could just be your answer, right? You could just say, ta-da, equals pi natural log 4. You know, game over, right? But if it's a multiple choice, you know, they could mess with you and they could say, oh, well, 4 is just 2 squared. And then, oh, look, we can take that 2 off the square and we can move that out in front, right? So any of those, you know, would be possibilities on a multiple choice. That's how they get you. Okay, so that was a dy example. And again, they won't all look like this. They're not necessarily going to give you the function x equals something in terms of y. The main thing to look for at the beginning is the same piece I was saying earlier. you're going to have to pay attention to what you're revolving around. Um, if you're revolving around the y-axis, it's going to be dy. If you're revolving around the x-axis, it's going to be dx. Okay, so here's another example. This is a super definitely calculator problem. So the natural draft cooling tower, shown at left, is about 500 feet high, and its shape can be approximated by the graph of this equation revolved about the y-axis. We're using a vertical axis because obviously this is a vertical scenario, but what they're saying here is they've already done a quadratic regression to find, right, this parabola. That is what this is. It's a parabola. It's just sideways, right? We've got y squared. It's a parabola. But they're saying if we take this parabola and we rotate it around an axis that represents the middle of the tower, then excuse me, then it's going to represent the volume of the whole tower. Okay, so that makes this my r, pi r squared h. So we can just do the pi times the integral from 0 to 500, because they're told it's 500 feet tall, and we're assuming that the units here are the same. So pi times integral 0 to 500 of this lovely equation squared dy. So again, there it is. This is what I'm talking about. Very, very easy to forget that square or the pi, right? Because you're used to just integrating stuff. Just do it. No, pi r squared h. Every time with volume of rotation, pi r squared h. This is a calculator problem. I'm not going to switch screens to the calculator because that is complicated based on the software I'm using. But here you go. So 24,700,000 cubic feet because it's volume, right? I started with linear feet for the height of the tower. I took a two-dimensional slice of it, and then I rotated it. So now I'm in 3 dimensions. So that's cubic feet. Okay. Okay, so in general, the disk method can be summarized with the following 2 formulas, both of which are based off the volume of a cylinder. So if you're revolving around the x-axis, so you're revolving around a horizontal axis, which means you're drawing in vertical little rectangles, okay, then that's going to be just pi integral r squared dx, right? So that's like if you have some typical curve, right, and you're rotating around the x-axis. So everything's in terms of x. But if you're rotating around a vertical axis, then everything needs to be dy, right? So same basic thing for both. The representative rectangle is perpendicular to the axis of revolution. So in other words, you draw in your radii. Your radius is perpendicular to the direction in which you're rotating it. So if you're rotating around a vertical axis, right? If you're rotating around a vertical axis, then you have a radius rectangle that you're then rotating around that vertical line. Okay, so let's actually work out some problems similar to the type of stuff you might see. The first thing you always want to do if a sketch of your region is not provided for you is to sketch the region. Okay. This one says, find the volume of the solid of revolution generated by revolving the region bounded by the graphs of y equals 2x squared, y equals 0, x equals 2 about the x-axis. So the very first thing that we're going to pay attention to is the fact that this says the x-axis. So that's a horizontal axis, so that means that this is going to be a dx problem. Good news. Okay, so if I sketch the region bounded by these 3 curves, if I think about y equals 2x squared, okay, so that's a parabola that passes through the origin. It's been vertically stretched a little bit, but it's still just a parabola at the end of the day. Y equals 0. So y equals 0, well, that's just the x-axis itself. Cool. And then x equals 2. That's a vertical line. Okay, so that means that I'm going to cross the x-axis here, right? This is y equals 0. We're going to cross the x-axis at 2. Okay, so the region bounded by those curves is going to be this kind of curvy rectangle, sorry, not rectangle, I know words, triangle in here. Okay, so the idea is that we're taking that kind of curvy triangle and we're going to rotate it about the x-axis. Now, it may or may not be helpful to you to draw more of this to kind of get a sense of what this means. And like I said, we're going to do a little bit of an activity tomorrow to kind of help you understand how this 2D triangle turns into a 3D shape. But this one is going to kind of look like a funnel. This is going to let me draw, maybe. I'll try and do it with my finger on this screen. This one kind of turns into a funnel type shape if I start rotating it around. Notice also, and this is important for some stuff we'll be looking at later this week, but notice that y equals 0 is the axis that we are rotating around, right? Y equals 0 is the x-axis. We're rotating around the x-axis. So that's significant, right? We are rotating this, again, kind of curvy triangle around one of its own sides. That's not always going to be the case. Okay, for disks, it is. We're going to be using this disk method whenever the axis of rotation is one of the sides of the figure. That's important. For our purposes, what do we need? Well, we need to figure out our limits on our integral. We know that our volume is going to be pi times a definite integral. Okay. So if we're doing dx, that means my limits are also x values. So I need to figure out my left to right, just like when I was doing area. Okay, so the left to right for my shape, on the left, the y equals 2x squared is going to equal y equals 0 at x equals 0. So that's my lower limit. My upper limit is where I'm stopping over here on the right, which is at x equals 2. So that 2 ends up just being my upper boundary, right? Because those are x values because this is going to be a dx. Okay, so I've got my a and b. Next I need r, and I'm going to square it, whatever it is, right? And if you want, it's not a bad idea to go ahead and write down parentheses squared, then plug in whatever radius turns out to be. And you can go ahead and put the dx back there too. Okay, so my radius, right, I've got all of these radii. They're being bounded on the bottom by y equals 0 and on the top by the parabola. So that's it, right? The distance for each of those is 2x squared on top minus 0 on the bottom. So 2x squared is r, because that's what determined the top of the shape. So that's the radius. It's 2x squared on top minus 0 on the bottom. Okay, so now I just need to solve this definite integral. So since r is always going to be squared, you're really always going to want to take a moment and simplify your integrand before you do anything to it. And a word of warning, we are also squaring this 2 right here because that is part of r. I'm squaring both the 2 and the x squared. So this is going to become 4x to the 4th dx. Now I'm ready to do my antiderivative. Okay, so and you can do the square brackets or not, you know, that's a personal preference thing, but this is going to go up to x to the 5th power. So I'm going to divide by 5. I could stick that pi up there with the 4 from 0 to 2. And while I'm dealing with evaluating this, it's probably just easier to pull that 4x, not x, 4 pi over 5. I'm sorry, it's been a very long day. Pull that over to the side and then deal with your fundamental theorem bit, your f of b minus f of a. 2 to the 5th power is 32. That's just 4 pi over 5, for those of you playing along at home. And 32 times 4, let's see, 32 times 2 is 64. 64 times 2 is 128. So this is going to be 128 pi over 5. Now, friendly reminder, only if it's multiple choice do you need to go that far. Okay, if this were an FRQ, you could stop right there. Right there. Beautiful. Because that's the point, right, where I have told them, oh, I know how to evaluate. This is f of b minus f of a, because that's calculus, right? That's the fundamental theorem of calculus. Once I show them that and show them that I understand the fundamental theorem, then I'm good. I'm off the hook, unless it's multiple choice. Okay, onward to the next one. Okay, so, Miss Smith, you're crazy. This is the same example. No, it's not. Find the volume of the solid of revolution generated by revolving the region bounded by the graphs of y equals 2x squared, y equals 2, and x equals 0 about the y-axis. Dun, dun, dun. Okay, so y-axis. Again, whatever my axis is, that's the first thing I want to pay attention to. If I'm revolving about the y-axis, that means this is a dy problem. Womp womp. They didn't give it to me in terms of y. That's fine. We're going to work it out. Okay, go ahead and graph it in terms of y equals 2x squared. Again, we already know what that looks like, right? We've got really it's a skinny parabola, but that's not really important for our purposes. So that's my first function here. Then I have y equals 2. Oh, that's different. Y equals 2 is a horizontal constant. We'll say that's 2. Then I have x equals 0. Oh, okay. Well, x equals 0 is the y-axis. So this is a totally different region, because what those enclose is going to be this one over here. Now, really, my setup here should have specified that it's the region in quadrant 1, and I meant to go back and fix that, and I didn't, and I'm not going to stop recording. But originally, it should say the one in quadrant 1. It doesn't really matter in this case, because y equals 2x squared is symmetric about the y-axis, but you know, whatever. In any case, the intention was it's going to be that region right there that I've highlighted. Now, we're revolving about the y-axis. You may find it helpful to, at the very least, draw in a loopy little circle to show what you're revolving around, to kind of keep in mind, okay, this is a dy thing, right? This is a vertical axis, so it's a dy situation. Okay, so I know that I'm going to have volume. There's going to be a pi, some integral of something squared dy. I just have to figure out all the rest. So first of all, because I'm in a dy scenario, my y values on my definite integral are bottom to top, right? So the bottom is 0, right? Because it's x equals 0 and y equals 2x squared. So my bottom is 0, my top is that 2. So kind of like before, right? That 2, the way it ends up serving its purpose is as that upper boundary. So now I need to figure out my radius. Okay. So if we think about how we would draw in our little radii here, if we're thinking right minus left. So the left here is just x equals 0. Emphasis on the x equals, right? Because the right is the parabola, right? Over here, this is the parabola. Okay, I need it to also be x equals something in terms of y. So, as I said before, they're not necessarily going to give you the function in terms of y when it's a dy. I need to put it in terms of y, so I'm going to just solve it for x, so that I have x equals. Okay, I'm going to divide by the 2, take the square root, x equals root y over 2. That represents this same parabola, because I'm in the positive part of it, right? So I could say that the right side here is being determined by that root y over 2. The left is x equals 0. It doesn't matter. Now I'm going to go, because that's r. So the radius there, on the right it's root y over 2. On the left it's 0. Okay, now I'm good to go. So as always, you're going to want to deal with your square in the integrand. So if I'm squaring a square root, that actually makes my life better because it gets rid of the root. Great. This is just 1/2 y. I'm going to put that 1/2 out here with that pi. Let him think about what he's done over there. Now if I just have y, and I do the antiderivative, power goes up to 2 and I divide. Okay, so now this is like I have a pi over 4 times y squared. I'm evaluating this from 0 to 2. Cool. 2 squared is 4, 0 squared is 0. Pi over 4 times 4 is pi. That doesn't look like a pi because I'm not used to writing on this board yet, but it's pi. Pi. Dang it. You get it what I mean. It's pi. Yay. So that happens every now and then. It's just pi. Or it's pi times whatever. Again, because we have that pi in the beginning, because the volume of a... So, oh, now I can write pi. Pi r squared h. Moral of the story. All right, one more. What is the volume of the solid generated by revolving the region bounded by the x-axis and the graph of y equals 4x minus x squared about the x-axis? So again, and I should have pointed this out more in the previous slide as well, but what I'm revolving about is one of the boundaries. So the previous example, the y-axis was the boundary, x equals 0. Now it's actually saying the phrasing this time, the same both ways, x-axis. Okay. Always want to sketch these first if a sketch has not been provided for you. I'm going to draw some happy little axes over here. Okay, so the x-axis is one of my boundaries. That's nice. My other function is y equals 4x minus x squared. For the interest of time, I'm just going to sketch in what that looks like. But if you wanted to know, for example, oh, well, where does this parabola equal 0? And you factor out an x, and you get 4 minus x, and my zeros are at 0 and 4. So over here on my graph, they are at 0 and 4, and it's an upside down parabola. Whee! Oh, that actually came out looking really good. Okay, so that's my region. I only needed 2 boundaries in this case because they enclose the region on their own. So that's also a possibility, right? It just said whatever region's enclosed by the 2 of them, that's this guy. Oop, that is, hang on, 0 to 4. So by kind of setting that equal to 0, what I was doing over here in the top right corner was I was saying, okay, if my functions are y equals 0 and this graph, I needed to find the points of intersection because those points of intersection become my a and b. So that is just like when we were doing area. I found the points of intersection. Now those become my a and b. Just like area between 2 curves. Same exact deal. All right. What do I need from here? Well, I'm doing volume of rotation, so pi integral. I've already figured out my 0 to 4, something squared. This is a dx because I'm going around a horizontal axis. I want to warn you against something here, and what I want to warn you against is just seeing x-axis and thinking dx. The reason that is problematic is because tomorrow we're going to look at ones where you're revolving around x equals 4 and it's dy. See what I'm saying? You can't just go based off the letter. Now the x-axis is y equals 0. Y equals 0 means it's going to be a dx because that's my axis of rotation. But horizontal line, dx. Okay, so I'm revolving around a horizontal line, so this is a dx scenario. That's how I want you to think about these. Okay, my radius. So my top minus bottom here is just the parabola minus 0, because the bottom is just 0. So that parabola is my radius. So all that is going inside that square. Let's see, if I hadn't put that square, I may see that my r ends in a square and have forgotten to put it there. So that's why I suggest you write the pi and the integral on the squared and the dx or dy first. Okay. So what do I need to do? Well, I need to FOIL it. Right, I've got multiple terms in my radius function this time, so I need to FOIL that thing out. So 4x times 4x would be 16x squared minus 2ab plus x to the fourth dx. Right, so if you're FOILing that, you're just multiplying it by itself. 4x times 4x, right? Take the product of the two and double it. Take the last one and square it. Okay. Then I'm going to do my antiderivative. May as well put it in order, right? So the x to the fourth, that's going to be 1/5, x to the fifth. Then that's going to be minus 2, x to the fourth in the middle. If I take that 16x squared, and whoop, hello. If I take that 16x squared, move it up to the third power, so I divide by 3. I just put them back in order, least to greatest. That's not necessary. I'm just a math person and I have routines. All right, so I'm going to plug in the 4. There's going to be a lot of simplifying here. I'm going to spare you some of that because this video is running very long. Sorry about that. Go away. Okay, so I've got this 4 to the 5th power over 5 minus 2 times 4 to the 4th power plus 16 over 3 times 4 to the 3rd. All of this is going to be minus 0. It's a polynomial, right? So all the stuff in the back just goes to 0. This one is presented as a multiple choice. I'm going to save us the trouble of simplifying it. You're welcome. I will say that ones that have this much arithmetic are not common features of the multiple choice. That is extremely time consuming without a calculator. If this were on the calculator section, well, my calculator doesn't do fractions. What do I do? Well, you get your decimal and then you see which multiple choice matches your decimal, right? I mean, process of elimination. Okay, that's it. Yay. I'm sorry this is a super long video. I really hate that I am out today, but hopefully I will be back tomorrow and then we can get back to normal. So thank you for watching so patiently. You've got a homework worksheet and yeah, that's it. Hopefully I'll see you tomorrow. And if you have any questions or anything, we should be able to go over those in class tomorrow too.